and we would directly jump in it. So if you have questions, use chat, raise your hand, do anything. If you're so active enough, just open your mic. You can also just speak. It's definitely welcome at this lecture. We are trying to create a very active and, let's say, interactive atmosphere here. And so don't be, let's say, restricted by any kind of existing thoughts you might have. So just give it if you have anything. All right, so this is our course, Materials Science and Engineering, and an introduction course for bachelor student. And let's move ahead. And this is a quote I like the most. I always gave it to almost all my students, all the lectures I teach. And it says, scientists discover the world that exists, engineers create the world that never was. So first of all, I would already like to ask you, who knows who said this sentence? So if you know, you can say it. You can also type in chat. And I will give you a few seconds to have a think about it. If you don't know, you also don't need to Google it because I'm going to tell you right away. So, okay, nobody knows. That's excellent. Because this sentence is given by the famous scientist von Karman, Professor von Karman. Maybe you know him. Yeah, a very great scientist in fluid dynamics and also many mechanics problems. And you see, this sentence is really emphasizing on the significance of engineers. Yeah, of course, the first part is also important, but I like the later part. Yeah, this is also, I think most of you are doing at this course. So you're probably from different schools, but I would say the main focus is probably engineering. Of course, I think we also have somebody from the science school, so don't be offended. Scientists are also very important. And so this course is gradually begin with, let's say, science stuff. That's why we're called Material Science and Engineering. But we will also move forward to engineering stuff. So actually we're covering both. So you will not be disappointed to just attend this course because you will learn both. And I would like to try to promote a lot on engineering side, on the creating side for all of you. So the starting point for this course is why we're emphasizing this, because engineers make things, and they make things or make them out of materials and using processes. So this is a common sense that you would probably already accept. So we are basically surrounded by things, except for your thoughts probably. And so what do they need to know if they want to make things? So if you are an engineer, what do you need to know? Let's say you want to produce, or you want to just kind of design or make a phone. So let's say an iPhone. How do you make it? So what do you need to know to make these phones? Of course, you know their functions, you know what they should basically deliver to the customers. But the very important stuff is how you're going to make it. So if I ask a question, do you know how many elements are used in this phone? So I'm not asking how many materials, I'm asking how many elements, elements from the periodic table. So if you have any idea, you can also just make a guess. So you probably don't really know the real number, but you can have a number in your mind, and I will try to give you the result. So this is about 46 elements, but I guess this kind of things are even getting a little bit more, because this was still the statistics based. I don't remember iPhone 11 or 10. So you see there are many elements in this phone. You probably know, okay, for sure, there's the cover, and it's aluminum most likely, and there's also silicon because I need the chip. But there are also many things you don't even imagine. For example, silver, iron, and niobium. So you're wondering, why do we need all this? So this is the knowledge that you need to know for let's say iPhone producer to produce an iPhone, because these materials are basic and all needed if you want to just produce an iPhone. And that's enough for what we need to know. So if you want to basically produce this one, so how do you choose this element, or how do you choose these materials? That's why we're trying to make sure you know the knowledge, about the materials and the processes, and understanding the material properties, because the material properties, they are the most important elements for you to make a function of it, for you to use it. And of course, you would be able to do a selection if you are, let's say, an iPhone engineer. And finally, you need information and the tools to be able to do the selection. So basically, this is a kind of short motivation for all of you to know why material science and engineering, let's say, matters. And what do we need to further know is, if you want to make things, you need to get those information and knowledge. And who will deliver those information and knowledge? That's the science part. Yeah, that's the scientists need to understand materials and design materials. And that's why we need both parts of the material science engineering. And what do they need to know before to give you, the knowledge about material science materials and the design materials? Basically, we need to have a look at this very important, let's say, material science engineering tetrahedra. Yeah, because this will be the central element. Let me get the pointer. And this will be the central element we're talking about for this course. So we will start with the structure. So here we're mainly talking about the microstructure of materials, but it also includes actually atomic structure, crystal structure, and finally arriving to microstructure. And then we're going to focus a lot on the properties. And then we're going to also move to performance. Finally, we're going to do processes, basically how to design processes to make this materials to change their structure to deliver different properties. And in the center, you can see this is a characterization. So this is something we need to basically quantitatively describe all these elements. So for example, when we just try to describe the structure of atomic structures, so you need to know what should be the, let's say, the forces, the kind of structure types we need to know. So this is so-called characterization. And when we talk about properties, we also need to have certain methods to characterize what is the mechanical property, what is other properties. So this is a central element for let's say, material science and engineering. And of course, nowadays, we're not only satisfied by, certain experiments to characterize certain properties. So as you know, the majority of this course is targeting, to the computational engineering students, but of course, we're also welcoming all the other students from different schools and majors. And the main feature is we, at the moment, not are doing just experiments. We're actually using a lot of computational models in the material science and engineering. And we're also promoting a lot of data. So this now becoming a really compound. So it's not just experimental characterization. Actually, we're doing the characterization by a lot of modeling and a lot of data. And so this, let's say, change actually making a very significant impact on the material science and engineering. We will gradually touch those differences. But speaking of this course, actually, we are giving you, let's say, knowledge about these 4 elements in the material science. And we're focusing in the center about characterization, but we're also teaching you certain computational methods or models for this course, in this course. So for you to be able to use them and to learn them in the future. And we're also trying to promote a little bit data related science into this course. So actually this figure you will meet very frequently in the future. So almost every course you will see it. And I hope gradually you really get the sense of it. Maybe at the moment you're just wondering, what is this very easy tetrahedral? And it will become really very fascinating for you when we just move ahead with different concepts and theories. All right, that's enough for a very short and basic opening. And now I will speak a little bit about who am I, and followed by, I want to also know who you are. So here you can see I was studying metallurgical engineering for my bachelor studies. So about 15 years, or no, about 20 years now. Yeah, at your age, basically. That was a university in China. So it's a University of Science and Technology in Beijing. And after that, I moved to RWTH Aachen University for my master study, and also a doctoral study, and also an early career. And during that, I moved ahead with basically material mechanics. So we made a lot of figures here. And during this, we also had a lot of interaction with MIT. There's a nice team working on ductile fracture and fracture behavior, basically on materials and structures. And I also came to Aalto about 3 years ago. And now I'm teaching you about material science and engineering. So these are the, let's say, business stuff. And I also gave you a little bit hobbies about what I would like to do. So traveling and food is primary hobbies. And in terms of sport, I like table tennis and billiard. So I'm looking for some good components from you, maybe. And also I do quite reading and music things. That's enough for me. Actually, now we would like to get started with all of you, because you know, you can actually learn a lot of stuff on your own. We're here to learn together. A very basic reason is when we learn together, there's a community factor. So I'd like to see who you are, and you probably will also get to know each other from this event, because there will be something very important for you to go through this course when you speak about assignments and so on. So the best condition is you know each other quite well, and you will do them in the group mode. All right, so this is a so-called camera game. I will start with a who question. So basically, I would like to ask, like, for example, who likes pizza? And anyone who is there can just open your camera and say yes. So if you like pizza, you say yes. And I will pick if you're multiple people, and if there's only one, you just open your camera and just say, I like pizza. And after you are picked, or after you switched on the camera, you will basically give us a short introduction about yourself. So your name, your location, your interests, your hobbies, and oh, I forgot to write about your major, for example, where you're from, so which major you are taking now, and at which grade. And then you will close the game. You will close your camera basically by another who question. So you can ask something you like. For example, if you like football, you can ask who likes football, or anything, yeah, just to give you some examples. And then you will, I mean, the next successor will come. You will pick the next successor, or if there are multiple, or maybe there's just one, and they will directly start. And we try to go through everybody of you. So after that, you know each other quite well. And if there's anyone who are left, and we will try to make you a small introduction as well. The basic line is let everybody to know each other. I think most likely most of you know each other in a way. So this will be the starting point. Let's go. So I will just continue with my question, but before that, I will first stop sharing. And okay, so we lost many students. Yeah. Okay, one more. But anyway, so what we're interested in are the ones who are staying. Yeah. So I will ask, who likes pizza? Ah, excellent. So Kim, you were the first.
Yes. Can you hear me?
Can you just give us a short introduction about yourself?
I'm Kim Nguyen. I'm a second bachelor. I'm a second year bachelor student in computational engineering, and I like pizza, obviously, and Italian food.
Awesome. And you can ask a question, or if you have something to introduce yourself, go ahead.
I think that's it for now.
Yeah.
I haven't think of anything else yet.
And now you can also ask a who question.
Ask a question like who likes pizza. So who likes math?
Oh, that's a difficult one. I'm not sure if anyone heard of it. King said, who likes math? Awesome. Just go ahead.
Yeah, hi everyone. My name is Jahanzeeb Naveed. Yeah, like I guess I have an on and off interest in math. Sometimes when I get what's going on, I really do like it. Sometimes when I get stuck, maybe not so much. But yeah, like when things are going, when you understand what's going on, it can be really fun to learn math. My major is computational engineering. My hobbies are, reading books, playing basketball, and just generally hanging out with my friends and normal stuff like that. And I'm very excited to take this course with all of you.
Awesome. Now it's your turn to throw out one more question.
To ask a question. Okay. Yeah. Who likes superhero films? That seems pretty easy.
Sorry, who likes what?
Superhero films.
Oh, I see. Cool. Is that your name? How to pronounce it?
It's Akın. It's quite difficult to pronounce, yeah.
Cool, Akın.
Yeah. Hi everyone, I'm Akın. I'm also studying computational engineering. I'm a second year also. And I do like superhero movies, but ironically, my all-time favorite superhero character would be Joker, which is actually a super villain. And my other hobbies are tennis and chess. Those two would be like my biggest hobbies. And I also really like food as well. Yeah.
No, Akın, you have to give a question before you go.
Question. Who here enjoys playing volleyball?
Volleyball. Now that could be a difficult one. Oh, I see someone is trying to give an answer? Awesome.
Yeah.
Zinola?
Zainullah.
Zenola. All right.
But you can call me Zain. It's probably
Okay.
easier. Yeah.
That's much better.
Yeah. My name is Zainullah, and I play sometimes volleyball. That's the basic. And I'm a second year student, so I also study computational engineering. And final question: who likes playing football?
That's a good one.
Mhm.
No one. Ah,
Hi, my
oh,
name
we
is
got.
yeah.
We got
My name
even two.
is
Yeah, you're the one. Daniela,
No.
sorry.
yeah. My name is Daniela. I'm from Portugal. I'm studying biomedical engineering, and I'm here for my master degree, 1 semester. And I like play soccer, so football. So I don't know.
You're in a master program.
Yeah.
Oh, I see. In mechanical engineering.
No, neuroscience. Yeah, it's not bad.
Okay.
So my questions is, who is here in Erasmus?
Who's here in what?
Exchange students.
Oh, exchange student. All right. Aramis. Good. You have one company.
Yeah, good morning. Good morning, Professor. I'm Alessandro Galiberti, and I'm an exchange student from Italy. And I'm a mechanical engineering student. And I'm here as an exchange student as well. And okay, that's it, I think. I don't know. My question is, who likes go to the gym and take care of his body?
Let's see. No. Jarab was already there. So now I'm a little bit confused. Who is trying to answer this question? No one. That's bad. Sandro, you have to ask another one because you didn't get any company from this course, obviously. You can try in a different one.
Is someone ever been to Italy?
If we already turned on our cameras, can we still like answer, or does it have to be someone who didn't turn on his camera yet?
We try to give chances to those who didn't answer.
Okay.
Yeah. So now we have Julia.
Hi, my name is Julia. My major is the built environment. And yeah, my hobbies are cooking. So I guess my question is, who likes cooking?
Cool. Oh, we have Wenchi. Wenchi was waiting.
Yeah. Hello everyone. I'm Wenchi Liu. I will be your TA for this semester, for this period of this course. And I did my master and PhD study in Aotearoa University, and I came to Aalto University in 2019. So it's already more than 2 years. And I like cooking. So my question is, who like Chinese food? I guess because some students do not have a camera from the partition list. So if you want to something, just turn on your microphone.
Yeah, that's a good point. So if you're unable to turn on your camera, it's okay. You don't have to leave. You can just answer, because it's good, of course, if we see you and you can know everybody as well. So not so far from. Oh, I think Ronfei must love Chinese food, right? You don't need to ask another one.
Yeah, I like Chinese food very much. Hello everyone, my name is Zhang Fei, and I'm very glad to be your teacher in the next few months. I really hope I could be your friend as well, but not only your teachers. Because this is my first lesson in my life. And thank you very much. And I want to ask a question. If there anyone like play computer games?
Oh, that's a good one.
Yeah, thank you.
No.
No, everyone likes studying now computer games.
No, come on. Nobody's trying to pick up that one. I don't trust you
Sure,
guys.
I'll pick it up, but I don't have a camera, sorry. My
Oh,
name's Lucas
Lucas.
Foley. Yeah,
Yeah.
I'm a second year bachelor in machine and construction technique. And let's see, I like playing computer games, going to the gym, playing football, like generally quite social, easygoing guy.
Cool.
And let's see,
You're bachelor or master?
bachelor.
All right.
Yeah. And let's see, my question is, does anyone like coffee here? I'm sure someone has to like coffee.
Oh, that's a little bit difficult. Not so many are fans of coffee.
Oh, impossible. We're in Finland. They have to like
Impossible.
coffee.
Nam,
Someone has to like coffee.
Nam, you were there. I think you were trying to pick up the computer game.
I tried to.
Now you have to go with the coffee. Sorry.
Yeah, I also like coffee, so it's fine. Yeah, hi, I'm Naman. I'm a third-year computational engineering student, and my hobbies are playing video games, playing football, going to the gym, occasionally like listening to music, and yeah, that's it. Also like coffee, but I prefer not to drink it too much because I have a sleeping issue. So yeah. So my question is, who likes rock music?
Nice. Oh, now we have one. Just go ahead.
Hi, my name is Errol Chainas.
Errol.
I'm a second year bachelor too. And yeah, I quite enjoy rock music. And my question would be, who here likes painting? Likes to paint?
Who likes painting? I think that's too artistic. All right. And you're oh, you have one friend.
Yeah, I like painting, but I'm more into sort of sketching and drawing. I'm Shreyas, and I'm a second year computational engineering major student. And well, I guess my hobbies are I listen to music, I draw and sketch and paint, and yeah, that's about it. I also play computer games as well. And my question is, well, who here likes to listen to music and sleep in general, I guess?
That's a good one. I think we don't have many left. We have.
Should have 4 left.
Samuel, William, and Incanson and Kay. So any of you likes music? Yeah.
Yeah. Hello.
Hi.
I'm Samuel Elqvist. I'm a second year student in mechanical engineering. and I like playing ice hockey and of course listen to music. And my question is, does anybody like ice hockey?
Oh, that could be a difficult one.
So,
oh,
hello.
good. Hi.
My name is Justin, and I'm an exchange student from France. I'm studying chemical engineering here in Alto, and I like hockey and a lot of sports. I practice rugby, and I also like to travel. So my question is, who likes to travel?
Good. That's a good one. And your exchange is for a bachelor program, right, Justin?
Master program.
Master program, mechanical engineering?
Yeah.
Okay, awesome. So welcome. Now I forgot because my screen has been changed. I forgot who wasn't mentioned yet. Was not, yeah. And William, yeah, William and Kay. So are you two guys here? If you are, let's just get you know. So William says, so he's not able to speak. That's okay. And Kay, who is Kay? So I'm not sure if Kane is with us. Good. I think that makes us complete with what, you know, in this list. So now I know everybody of you who are here. And I see the majority is from computational engineering. Of course, we have also 3 or 4 exchange students. So welcome you very much. And I hope we'll really have a nice journey here in this course. Just a quick question for the computational engineering guys. You know, you enrolled last year when everything was closed. Have you managed to meet each other, form a group, you know, stuff like this? Not at all. So everything was online?
Yeah, everything was online. And on top of that, even still, like, I think most people are outside of campus right now. So yeah, I mean, so far, very few of us have been able to get to know each other. And yeah, that's kind of like one of like the biggest downsides of COVID, yeah.
I see. Do you have some study groups? Maybe.
So sometimes like when we get like we have similar courses, so sometimes when we get stuck in problems, we do ask each other. I'm not sure if there are any specific study groups that we have, but we do like ask each other for help from time to time. Yeah.
Good. So in this course, you will learn a little bit more during the exercise session, but we're trying to promote at least pairs. So of course you could do everything individually, but now we really realize it's becoming very difficult, you know, with this online situation, that you don't have chances to meet, and also very easy to entering a, you know, struggling phases. So we try to promote you to study in 2 group, you know, in a group with 2 people, not more. 2 is the best. So for you, I would promote you try to get, you know, a, let's say, material science engineering buddy, and you can do this together. And especially for the visiting students, it will be a little bit more difficult for you to do this. But I think we have the My Courses system. You know, you can try to really get to know each other and form a study group if you wish. I, from, you know, teaching this course for already last year and also other courses, this will be a very good help for all of you to, you know, get through this course and just pay attention to each other's emotion, health. You know, this is just a very short 7 weeks for this course. But if you find a good friend in terms of studying, you will benefit for a long period. All right, now we will stop this game so you know each other, you even say some faces, and you have some common interest in something, and try to be, let's say, initiative. Yeah, you can just find someone to hang out. Okay, now let me go back to our course slides, we will just try to go through of it, and then we will start a short a break. All right, good. I hope everybody sees my screen back, and now we continue. We will continue with the introduction of this course. I will keep this part very short, because many terms for you are completely unknowns. But anyway, I still try to give you some pieces of it, and you will gradually pick them up. You know, the course objective basically is to introduce you fundamental concepts in material science and engineering, and the learning outcomes are the following. First, to distinguish and explain terms in material science, and to relate material structures to properties to understand influence of processes on structures. If you just paying attention on the tetrahedral, I try to explain to you, actually I'm already repeating those 4 elements in this part here. But before we really go to this detailed issues, I would like to give you a quick difference between this course to the others, especially for, let's say, the mechanical engineers and computational engineers. Because this course, material science engineering, is not like, you know, the solid mechanics or continuum mechanics, fluid mechanics, and all this stuff. You know, very mathematical driven, and the equations regulated. Everything is built, you know, on top of each other. So you really start with the very basic foundation, and then you go on and on. Material science engineering, they're a little bit less systematic. So you have to imagine it like a big puzzle pieces, a big puzzle, and we're just learning pieces by pieces. So I try to make this learning process more systematic, but still you would see some cases not very strong connection are there. So it's like you're doing a puzzle. You know, you start with something, you go along, and probably you enter it adding, you start from another area, and you start to do this things again. And this is very similar to what we're going to learn here. So that also means if you miss 1 piece or 2 pieces, that's fine. But if you miss too many, that would be a problem. So for this part, you need to a little bit adjust your way of learning. It would be fun. Yeah, it's really like making making a puzzle. But you also would be able to distinguish the learning pattern from this course, you know, to your let's say mechanics courses. And after learning to a certain phase, you will be able to do some analysis. You know, you will be able to analyze deformation, strengthening, and failure mechanisms, brittle, ductile, fracture, fatigue, and all this stuff. And finally, we try to make sure you could also relate, you know, processes stuff. This is about diffusion, precipitation, phase transformation to microstructure changes in materials. So all of this are unknowns to you. Don't mind, you will just learn them step by step. And the last part is something new, especially for this course I'm doing here. So the unique part of this course compared to all the other material science and engineering courses in the world is we're implementing a lot of computational science into this course. So you will see most of this from the exercise. I have a few slides to show you. This is a part you will benefit really a lot. So I strongly recommend you to follow and get those exercises. And the last part is about to read the material science literature and journals. This is kind of specific strengthening about your, let's say, general ability to write your bachelor thesis in that. And our study material is this textbook, you probably know from the famous Callister. So the material science and engineering and introduction. As far as remember, we don't have a ebook, you know, of this specific course, specific book in our Autofina library, but of course there are physical books. So if you would like to read the physical books, don't hesitate to go there to borrow. That's no problem. But if you are not here around or you don't like to read physical books, you could also get it very easily online. I cannot provide you the link, but if you just pay attention to this slide, actually you would be able to find it. We don't have the ebook in the library. That's the unfortunate part. But as I said, you can easily find the ebook just from Google or something. And we also have 2 other books to recommend. So if you would like to really dive deep into the subject, the following 2 books would be helpful for you. But this is not mandatory. So they're really going to a little bit deeper in material science. So you would have physical metallurgy and advanced materials. Excuse me. Let me just try to answer that. All right, that was a reminder for our break. Good. So those are the 2 following books if you have interest to this, to more knowledge. And a little bit about our class structure and times. So we have the lectures always Mondays and Tuesdays for the next following 6 weeks, from 10:15 to 12. And then we have emphasized really very active discussion and participation, as I just told you at the beginning. So now we have a very based understanding about each other. So I hope you could really actively attend this course. And then we have the exercise session. As I told you, a very nice exercise session. I will speak a little bit into that in detail later. This will happen every Thursday. So also the same time, 10:15 to 12. And the exercise will help you to solve, the learning outcome related tasks and assignments. And most importantly, it will give you an introduction and even a, let's say, hands-on tutorials on computational based tools and how to use them to solve a computational related task. So I have to tell you, this is a very unique part of the course. And at the beginning, you might feel these tasks are really just falling from the heaven. You don't know what we are using or what we are doing this. But actually, you will really benefit from it if you start doing something at your work and at a, let's say, research assistant position or so. Because this materials and these sessions, you probably need to pay to learn when you just at the work or so. You need to go to workshops, you need to go to conferences to get them. And now we're trying to really give it to you during this exercise session. I'm sure you will benefit a lot from these exercises. And then we have weekly assignments. This will basically driving through you to learn or to get all the learning objectives. It starts every Monday, and the deadline to submit it is 6 p.m. on Sundays. It will be published on my courses, so I think you know the system pretty well. And you will just pick up them there and you will submit them there. In addition to this regular, let's say, things, we also implemented a Q&A time, and this is happening on Zoom as well. So every Tuesday, so afternoon. Just in case if you have specific questions, you don't understand something from the lectures, or you would like to know something in detail about assignments and so on. So try to go there. And this is an additional time. Miss Menchilu and Rongfei Juan will be there to help you out. So they were really there trying to solve the issues or problems you are facing. So if you get issues, don't forget to be there. And finally, of course, is the general discussion on my courses. You can participate at any time. So we all very much encourage you to be there and just ask any questions or even answer any questions that your peers ask. And of course, we will also try to help you on that platform. Some central times of replies are allocated to Wednesday, Thursday, and Friday afternoons. So you can ask them anytime, but you will most likely get answers from these times. Finally, we have the exam that will be in the final week. We will most likely have an online exam, of course, and it will be most likely half written and half oral, as we did last year. And what we cannot forget is the independent reading and learning, individually or in group. Yeah. So actually, this part will be the, let's say, the major time you need to spend on. So you can see the left part is really just a few hours per week, but we need you to concentrate to solve the assignments and to learn the book and to solve problems together. Or individually or together. I recommend very, very much you form a study group and do that together. Good. So this is some very quick, you have already seen this from my courses, very quick going through about the concepts we're going to have in this course. Once again, you might feel a little bit unfamiliar with all these terms. But believe me, you will just get to know them very nicely later. And I will not explain in detail because we're going to go through them week by week. What's more important is you need to pay attention to what is the chapters connecting to the concept in this book. So if you have anything specific, you can try to visit that book. I promise you to explain a little bit in detail about our, very nice exercise sessions. And these are some slides to give you, let's say, a quick look at this. In the exercise 1 and exercise 2, so basically the exercises from the first 2 weeks, you will learn a few, let's say, computational tools. And the first week, you will get to know a material or microstructure analysis and characterization tools. So this is a rather standard tool, but here this MText is a toolbox from MATLAB. So people are familiar with Python or MATLAB, you would be able to enjoy this tool very much, because with this tool, you can really create very nice analysis and about your microstructures, and create also interesting figures about your microstructure, about your materials. And the second week, we will have a exercise on a virtual microstructure. So this is so-called representative volume elements. So these are the figures you're looking at here. And because we have our materials in the reality, if you want to do computational related tasks, the first thing you need to do is transfer your materials into your computer. And how to do that? So we have a software for you, and you will learn how to operate on the software, and finally you will be able to generate your cute RVEs, 3D rotating RVEs on your own. So this is the work, by the way, from Ms. Winchidu, and you will learn how to do that from this course. And in the third and the fourth week, you will basically learn, let's say, finite element related stuff. So this is a crash box simulation. Actually, the guys just 1 year earlier than you now are producing this stuff. You will not get that deep in such a fine resolution, but you will learn basic about FEM and most likely learn how to deal with a, let's say, plastic deformation condition. And here is about failure. So this is a failure under impact for lithium ion battery. So very hot issue at the moment as well. And in the fourth week, you will finally move to, let's say, process-related exercises. And this is exercise to tell you what is phase diagram and how do you kind of visualize or calculate your microstructure evolution during a process. And the fifth week, you will learn about, let's say, material selection. So basically, if you know the material properties, you know the material processes, and now I want to design something, a chair or a bottle, and how should I choose my materials? Should I go with the glass or polymer, things like this. So there's one tool behind it. It's called selection of engineering materials. You will be able to get the sneak peek about that. And finally, it's a multi-physics and multi-scale modeling session. But this probably will be a little bit optional because we realize this is the last week. You most likely need to prepare your exam in a more extensive way. So I said this exercise will be, or this computation exercise will be rather optional. Let's see the progress at that time. All right. So then quickly about the course grade. You basically during the course you will be collecting points. We will try to dedicate these points into 3 or 4 sections. The first part is about the participation. So as you can see, you will basically earn 10 points from attending lectures, seminars, exercises. So for each session, those sessions on Monday, Tuesdays, and Thursdays, you'll get 0.5 points. And in addition, if you just active participate on the forum, you'll get 1 more point there. And the majority of the points will be given on the assignments. So in total, you will have 40 points for the assignments. And for each week, you will have mostly 7 points, except for the last week, that will be only 5 points. That is related to removal of the computational exercise over there. You will learn a little bit detail during the exercise session. And then we have 50 points on exam, so nothing more to say about that. Something special is we have 10 points on actual activities. So as you can see, before this 10 points, that's 100. And this 10 points are really used to help you with your grades. So if you're able to perform those additional 10 points, you will basically get 110 in maximum. That will help you to improve your grade into some good ones like 4 or 5 or similar. As you can see, we set our passing grade is 50, which is rather easy to achieve. So I hope everybody could enjoy this course. You might have different orientations in your study path or in your career path, but I think you would be able to get good results from this course and carry on with the rest. All right, that's the course grade, and now I would like to ask if you have any questions, for the content up to now. I have something in chat. The lectures recorded. Yes, lectures are recorded, but the recording will not be shared with the public. You should be able to get all the slides from the course, and that will be your main materials to use. Good. Now let's have a short break, something like 5 minutes. Then after that, we will continue with some, substantial things of this course. Okay, so let's be back in 5 minutes. So now it's 11:13. We will start our second half in 11:18. All right, so see you guys later. All right. That was a rather short break, but I hope everybody had a fresh after this first session. And actually, I realized I have something unfinished from the first session. And it is very important, actually. So I would like to just give you a quick, let's say, feedback about this. So that is about 3 tips I would like to give you at the very beginning of this course. And I hope everybody pays attention to it. So the first tip is about this iceberg. So I think everybody knows this picture, and I hope you could really imagine this picture as any problems in your life, or the course that we're facing right now. So you should realize that, you know, the substance of this course of any problem is always different from what you look at on the surface. So just be prepared. You will discover something uncertain. It could be interesting. It could be a little bit challenging. It could be fun. It could be also disappointing. So be prepared that you will see this uncertainty in any problems or in any, let's say, learning processes. Be prepared and you won't be surprised. Yeah. And the second tip that I would like to share with you is this wisdom and confidence figure. You know, if you look at the x-axis, it's the wisdom or knowledge, and the second the y-axis is your confidence. This is something you might very easily see in any learning process, especially when you start something new. You will easily kind of enter this peak of mountain stupid. Yeah, because if you know nothing and you get something, very soon you say, oh, this is very easy. I'm very confident now. But be careful there, yeah, because very soon after you will enter this so-called valley of despair or valley of, let's say, depression, and you will lose your confidence and you will lose hope on this lecture. I can guarantee you that in this lecture, this moment will come very, very soon. So most likely today and or tomorrow. So probably next week, latest. So you'll get this peak very soon. And that's the part. So some of you might already say, okay, I will not get recovered. I will quit. But actually, if you just hang out there and continue developing, you will soon just gain the momentum and enter this so-called slope of alignment and finally go to this plateau of sustainability. So this is the point we want to bring you to. And what is required is to realize this is a learning curve that everybody has to go through. No one can skip from. If you know this, you will feel much better because when you are here, you know, I have nothing to lose. If I just continue, I will just grow. Yeah, so this is important figure for everybody to remember, not just learning this course, but learning everything in your life or solving any problem in your project or future. So this is the second tip. And the third tip is so-called 10,000 hours rule. So of course, this 10,000 is not projected into our course here because the 10,000 hours rule is used to become an expert on something that is really to make life on. And so that is connect to your future job or future career. But the kind of meaning is very similar to what we need to get you implemented in this course. So we don't need 10,000 hours for you. We need round about, let's say, 135 hours. So plus minus 20 for some statistical reasons. So this is the hours you should invest on this course and have a vision about it and calculate how much that is converted to hours, days, weeks, and so on. The most important information is get started now. Don't wait until the last moment to study on this course. And those are the 3 very useful but very important tips I would like to share with you before we begin seriously on this course. And I hope you enjoyed it. Now we will get something which most likely bring you to the valley of despair, but I know you will go through it. All right, so this is the main concept of our course, and this is the beginning of it. And what do we do for the first chapter or the first lecture? And we will get a very easy starting point. So I try to tell you what is material science and engineering, and why are the material science or materials important, and what is the most important thing for engineers to understand materials. So very easy stuff to let you know material science and engineering is really something you need to know. And afterwards, I gave you some knowledge about typical material types, material properties, and structure property correlation. So I think this is just to give you a connection between what we're learning here with what we're gonna do in daily life. So let's say I can try to give you a picture about what material science and engineering about. You know, material science engineering is a very interdisciplinary subject. So everybody might have different opinions. So feel free to use the METI with this code to give your own opinion. So you can use just the 3 words to describe what material science engineering is. It will be interesting for me to see what is your idea. And this is more like a official definition, or some definition I like most. First of all, material science engineering or material science is a very interdisciplinary subject. It is basically a combination between physics and chemistry. So as you see, the first part, we will start with solid, atomic bonding, electron behavior, and so on. This will be covered right away after I gave you some importance about material science engineering. And of course, we also touch a lot about physics, mechanics, and we also go with the liquid and gas, you know, about phase transformation and so on. So it's really a combination about many pieces of knowledge and let's say information together. So that's what I told you at the very beginning. We're really touching many pieces in the material science and engineering, and finally try to build up a puzzle. And this is a basic image about material science and engineering. And you can see we have already spoken about material science and engineering. What are the differences at the very beginning? Here is a more detailed explanation about it. So material science, to be more specific, is to investigate the relationship between structure and properties of materials. If you just look at this tetrahedral. So here, once again, we start with the structures and then we arrive at properties. So the properties of materials are really decided by the structures. So one of the main tasks here for our study is to be able to understand the correlation of these two. So you're spending more than 50% of your time trying to understand these two guys. So the correlation between structure and properties. And then we can also go forward to processes and performance, because performance is nothing but combination of properties together. And then we will go to processes, because processes is so important, because processes will decide on the structures, decide material structures. And if we just know, this correlations between these 4 elements, we'll be able to design or develop new materials. So this is about material science, trying to figure out the correlation between all these 4 elements together. And the material engineering basically is something we're looking at the outer layer of this figure, because that is related to creating stuff that never was, right? So basically we need to create products from other existing materials, via, let's say, cutting, via shaping, all these tools, or we develop material processes technologies. So basically this is related to, for example, processes via heat treatment, processes via surface treatment, and so on. And another point is we also try to do the selection. That is a most important part of material engineering as well. When you design product, you need to do material selections. Yeah. So this is a basic explanation between material science and engineering, and why materials are important. So this is, I mean, everybody could have all different reasons. This is a very basic one because maybe you know our society is more or less noted by materials. So you remember the Stone Age, Bronze Age, Iron Age, and nowadays there are many different ages like Silicon Age, Nanomaterials Age, Polymer Age, and even Hydrogen Age at the moment, most likely. So you can see materials are just relevant to the basically the human history, and it is also everywhere, you know, in our daily life. All the different, let's say, industry sectors or daily life around. Basically, you need to realize anything via materials. You know, even for software engineers, you also need the hardware to carry on your algorithms and products. So this is why materials are always so important. And of course, if you want to become a materials engineer, you know why materials is important. But if you say, I'm just trying to become an electrical engineer, I become a mechanical engineer, I don't need to care about so much about materials. That is also not entirely true. You know, I have students who majored in material science that are now working at Amazon, for example. You know, even for Amazon or Facebook, don't mention Apple or these companies, they all hire very significant amount of materials engineers or even normal engineers with material science engineering background, basically because, you know, you always need materials to realize your products, devices, components. That's why, in general sense, as any engineers, you need to know the basics about material properties and try to understand the structure property relationship. Okay. I think that really gives you some significance about material science and engineering. So here I gave you a very simple example about the correlation between process, structure, and problem, because we were only speaking, you know, abstract stuff for almost 1.5 hours. And now I need to give you one example. And this example is related to steel production. So a very specific but so common business. We're looking at is so-called cooling rate and hardness. So this two probably both sound a little bit strange for you. But I think most of you have some cooking experience. We have, you know, 2 or even 3 students here who like cooking. If you have baked a cake or something like that, this process that we're producing steels, of course, steel production is a very long process. But at the end of the steel production, it's something called heat treatment. Basically, you put your steel into an oven, you heat it up, and then you hold it for a while, you cool it down. It's very similar to cooking or to bake a cake, something like that. So here I'm trying to tell you one parameter, which is called the cooling rate. Yeah, and only this simple parameter could make a huge impact on your properties and all your structures of the material. The easy thing you can realize is when I have very fast cooling rate, so you don't recognize what is what, you know, from the small cute pictures, they're telling you what the microstructure is. You will be able to really understand what they are after this course. So this is the amazing part about learning. Yeah. At the moment now, you know nothing about it, but you will just know that in 6 weeks. But what you should pay attention is, I don't change anything. I don't change my oven time. I don't change my holding time. I don't change my oven temperature. I only change how fast I cool it from an elevated temperature to room temperature, let's say. And one is very fast, so about 1,000 degrees C per second, and one is pretty slow, about a few seconds or even less a second per second, less a degree per second. You see the microstructure change dramatically. Yeah, so as I said, if you have some cooking experience, you might feel familiar with this. For example, you have a cake in the oven and you cool it in your oven without moving it, or you just take it out to a very low, I mean, even not very low, just a little bit low refrigerator, you will see the difference. So in one case, your cake will be pretty soft, and in another case, your cake will be pretty hard. Yeah, you probably know this from practice, but you might not know the mechanisms. And here we're trying to tell you what is mechanism behind, why the processes are really controlling so significant to your microstructure. And finally, it is measured by the hardness. So we have a specific unit. Don't worry if you don't know it, you will know it later. Let me get the pointer as well. But I think everybody knows the philosophy, especially when you just make an analogy to cooking and you see why processes are decisive to your structures and your structures are deciding your properties in that. And this is very important. So try to keep this example in your mind, and the whole course is basically to telling you why these are connected and how you could connect them. Then some typical materials we are dealing with during the course. The first thing is, of course, metals, because this is the most widely used engineering materials in many businesses. Some very, let's say, typical properties already. You can describe metals, so they're strong and ductile and high thermal electrical conductivity. And also in terms of optic properties, they're usually opaque and reflective even. Yeah. And then the second class of materials we're talking about will be polymers and plastics. So they are non-metallic materials basically. So rather soft, ductile, also very widely used in our daily life. So low density, low strength, and low thermal and electric conductivity, and also could be opaque and could be translucent or transparent, and so on. And the third class we're gonna touch is about ceramics. So this is also compounds of metallic and non-metallic elements. Could be oxides, carbides, nitrides, sulfides. So if you're not familiar with all these terms, don't worry. We will also get to them step by step. Yeah. So it could be hard, brittle. So brittle means they're easy to break. And low thermal electrical conductivity and optical properties are also varied. You see, these are the three categories of materials we're gonna touch. We put main emphasis on metals and a little bit less on ceramics and very little on plastic and polymers, because we cannot talk too much. And as metals are the most important materials in terms of engineering applications, so we focus a lot on metals. And some typical properties we're speaking about. So we will start with the mechanical, and we'll also go to electrical and thermal. So I guess we have some electrical engineering students, so you will also learn about electric properties. And there are also, let's say, magnetic, optical, derivative, and we will pay less attention to the last three. So as I said, mechanical is the first principle or the first thing we look at, and then we focus on electric and thermal as well. And this is a very simple diagram to show you the mechanical properties and what is the correlation between, let's say, the hardness and also some structure level, atomic structure level, alloying differences. So this is a correlation that you would draw already. So I don't explain in detail, this is very similar, or a similar concept at least, to the steel process I just introduced you before. And this is something about electrical. As you can see, we're changing the different properties. So this is not harness anymore, because for electrical properties, we're speaking about conductivity or resistivity. But what is common is we always try to find correlations between properties and their, let's say, processes, yeah, or their structures. So here we're talking about their atomic structure, how the alloying design is different, and that will change the properties significantly. So we'll not go to details right here. Once again, you can have a look at it. And now I try to give you a quick summary about the first part that we already went through. It's very simple. It's nothing about to tell you what is material science and engineering, and why we need to understand the correlation between materials and their properties. And you probably now know better that the correlation between structure, process, and properties with a steel production example. And you also could see some typical, let's say, materials we are investigating in the course: metals, ceramics, polymers, and also some typical mechanical properties we are talking about. And that's the first part of the course. So I think now you realize, good, I'm feeling comfortable. Everything spoken that already I know very well. And now we will start something a little bit more challenging. So be prepared. As I said, you will see this picture very often during the course. And this is actually guiding through the structure of this course. So how we begin with, so we will start with the structure. Yeah, as I said, we will start with the structure bottom up. So bottom up means we will start with something small and build knowledge about it, and we go upper and upper. So we go bigger and bigger. So what is something small? So small is about atomic or even subatomic level. That's where we're going to start for today's lecture. And of course, when we study about structures, we always want to make correlation to properties. So for small issues, they're not that decisive, or they're not that fully reflected in their properties, but you will see some hints. Yeah, you will be able to understand many things after the next, let's say, 20 minutes of the lecture already. And now let's jump into it. So the chapter 2 is about atomic structure and interatomic bonding. This is a topic you are mostly pretty familiar with from your high school, most likely. But just in case you already forget some of them, I try to give you a, let's say, recap. That's why we're gonna kind of go through it rather quickly, because I think you know the knowledge pretty well. You just need to remind yourself about it. So we will touch in this course about what is the structure of atoms and what are the characteristics of the atoms or molecules, their interatomic and intermolecular bonding. So these are the major topic of today. And especially what types of this interatomic or intermolecular bonds exists. And finally, we will try to tell you what properties of these bonds will influence in our materials. And the first slide is something pretty basic, is what is atomic structure. I think everybody knows about this. So atom is a word generated from ancient Greek, meaning something not to be divided or something not able to be divided. But actually, with the recent developments, everybody knows atoms can be divided like crazily. Yeah? So the first thing we know is there are electrons and nucleus. So nucleus are divided into protons and neutrons. Actually, you can also divide those guys even further, but we're not going to talk about that. And some basic concepts is about atomic number. So this is number equal to the protons number in the nucleus of atom. And another issue is about atomic mass unit. So MU, this is the 12th of the mass of carbon atoms. And there's another very important concept similarly is so-called atomic weight. Yeah, so this is different from atomic mass unit. So this is basically the weight when you just have a large number of atoms or molecules in your material. So this number probably something you should keep in mind is the so-called Avogadro constants, Na. So with the unit of mole to the -1. So these are really basic issues we addressed in your basic, let's say, high school courses. Try to get a reminder of it because we're gonna do quite some calculations based on this. And the other important concept is about electronic structures. So we know the property of atom is decided, except for mass, of course, but other properties are not decided by the nucleus. Yeah, they're decided by the electrons. The electrons have, you know, from quantum mechanics, have the wave-like and particle-like characteristics. So we can go really deep into this topic, but I would give you some really rather brave and summarized content about this electron properties. So there are 4 important quantum numbers about electrons. They're trying to describe, you know, the probability function of the electron. You know, electrons are not like, you know, the nucleus. They're having a stable position in the atom. So electrons are basically moving around. It's a probability density, a function to describe its shape, size, and orientations, and so on. We will not focus too much about orientation and their shape, but what we're focusing on mainly is about their position. So there are 2 important, let's say, quantum numbers to describe. The first one is, let's say, the principal, meaning which shell the electrons are located. Yeah, you know, the electrons are always located on specific cells. So the principal ones are KLMNO. Yeah, and the second one is so-called subshell. So this is meaning in one primary shell or principal cell, how many subcells I could contain. This is the second number, and they're described by SPDF. And what do they mean? In nutshell, basically, you can visualize from this picture. If I have my nucleus inside, and then my electrons basically will be just surrounding it with all these cells. So each circle here is representing one cell. You know, the electrons always try to stay on the discrete energy values with these discrete cells, and they try to stay as minimum as possible. So you can see here the lowest cell, this is the K shell with just one subcell, and one subcell will correspond to electrons, you know, the Pauli principle. And this is the lowest energy. So the electrons will first try to fulfill here. And if it's full, it will go to the second energy level. And if this is full again, it will go to the third energy level and so on. So basically, you know, each subshell will contain a pair of electrons. And for the K shell, the full condition is 2. But for, let's say, the L shell, the full condition is already 8. Yeah, you know, there are 4 subcells, and each subcell contains a pair of electrons. Then you have 8. And this applies to many shells as well. That gives us a description about electrons. So if they're stable or not stable. So what is stable means, you know, the outer layer of the cell is fulfilled. That means the electron is stable. And if it's not fulfilled, it is not stable. Yeah. And as you can see, the outer shell electrons are so-called valence electrons or valent shell. Yeah. If we're talking about hydrogen, yeah, the outer layer is the 1s. Yeah, the first shell is the K, and the subshell is S. We have only one electron. That means this is 1s, 1. So it's not full. Yeah, it's not paired, the electron. So it's not stable. When you go to helium and you have two electrons and they're exactly fulfilling the valence shell, so the K shell, there are 2, so it is stable. And this can go on and on. So if you look at the second stable is about neutron, and we have 8, let's say, electrons in the valence shell, and that is also stable, and so on. Argon is as well. So as you can see, most of the elements, they're in unstable condition, and only just a few are stable. And this electrons that in the most outer shell is so-called valence electrons. And if they're fulfilled, that's good. If they're not fulfilled, so you would have a tendency when they're not stable, they would rather to require electrons to become stable, or they would rather to lose electrons to become stable, because all the elements trying to get their stable case. Yeah, this is the nature of all the elements. That's why we would have a description about their stability. So as you can see, this is described most likely from the periodic table that you are familiar with already. So if we just look at the most left of the periodic table, you see these are basically metals. So the metals are always having, the valence electrons with 1 or 2, something like this. And they're very easy to give up the electrons to become stable, because their valence shell is always having 1 or 2 or 3, let's say, additional electrons. And if you look at the right-hand side of the table, on the most right-hand side, the column is the inert gases. So they're the elements which are in a stable case. So their electrons are stable. So that's why they're inert. So they don't want to give up, or they don't want to receive, let's say, electrons. But if you just look the column towards it, so this is the column that is having, let's say, 6 valence electrons. So they're very easy to be stable if they just accept 1. And this is the guys that having, this is 7 and this is 6 valence electrons. They will become stable if they receive 2. So as you can see, how to describe their kind of stability, and we have this so-called electronegativity values to describe. So if you have a electronegativity rather small, so this is here the slide, a small value of electronegativity, meaning you tend to give up electrons, and if you have a larger electronegativity, the maximum is 4, and there's tendency to receive electrons. So what do we need this electronegativity? Because that will be able to tell us how to describe the bonding system. So if there 2 atoms are meeting each other, for example, one is the metal atom and the other is the non-metal atom. So if they have very dissimilar electronegativities, and the metal atom will be likely to give up their electrons, and the non-metal will just receive electrons. So the example is given here. So magnesium oxide. So as you can see, the oxide will receive these 2 electrons to become stable, and the magnesium will just give up these 2 electrons to become stable. And this process is so-called ionization process. And it will produce the first important bonding, which is so-called ionic bonding. And this is a very strong bonding, as you can imagine probably. And the example is also sodium chloride. As you can see, between these 2 let's say, atoms after the electronic exchange, you would develop a very strong Coulombic attraction. And there's also a energy state to describe this, let's say, this attraction, because the final energy will be decomposed into two parts. So, you know, we have the attractive part, we also have the repulsive part, but the entire energy is decided by basically the sum of it. And the atoms, the two atoms will become stable when this energy, the net energy, is reaching the minimum condition. Yeah, once again, you know, always our materials atoms are trying to reach this minimum energy state. So here it is. And you have a equation basically to describe this full energy. So here it's given, and it's a function of this two energy, and it's also a function of the, let's say, the radius, the interatomic separation distance between these two atoms. And this is the ionic bonding. So you can see when we just produce, when we just bring metallic and non-metallic atoms together, we were likely to produce this kind of ionic bonding. And you can see most of the ceramics are corresponding to this type of bonding. You might then ask, if we just bring two elements that are having similar electron activities, what will happen? So here is an example given by hydrogen. So you see two hydrogens are meeting each other. So they're both in unstable condition. And what do they do? So they will develop the second most important bonding. This is so-called covalent bonding. So nobody will give up or receive their own electrons. Rather, instead, they will try to build up a common state that they will share their kind of valence shell. So in that sharing process, both of these two atoms become stable because they will have two as their valence electrons. And then you will become this kind of covalent bonding. And as you can see, these two types of bondings are not really significantly distinguished from each other. So in the most cases, you could develop a mixed bonding. So when you have an element meeting an element, so they're not so different in terms of electron activity, but also not that similar. So what will happen? And they will most likely develop a mixed bonding type. And we have this variable, so-called ionic character. So based on the electron activities of A atom and B atom, and you can always using this equation to calculate so how much the covalent bonding will be developed and how much the ionic bonding will be developed. So this is a concept you should be familiar with already. And we will also require you to be able to master this concept via some calculations. So that's all about, you know, non-metallic elements. And now we talk about metallic elements. So when we have metallic elements meeting each other, what will happen? So that develops our third most important bonding. This is called so-called metallic bonding. Actually, this is the simplest one, because when you have metallic elements together, you know the electrons, they will be not so bound to each other. They will be delocalized and form the so-called electron cloud. And basically they're everywhere and they're always in kind of interaction with iron core. So you will see this is our, let's say, the core elements, and these are the C of the valence electrons. And the bonding system will be developed by this metallic bonding. So this is a very brief introduction. As you can see already, probably, this kind of bonding is a little bit less strong than the previous two. Yeah, that is true. Those three are the most important, let's say, mandatory primary bonding. And we also have certain secondary bonding. So the secondary bonding are mainly characterized in two. The first one is so-called fluctuating bonding. This is developed from the dipoles. The very famous one is the is van der Waals, bonding. Everybody knows, yeah. And the second one is little bit very famous, is the permanent dipoles. This is mainly kind of existing in liquids and or in polymers that you will develop. The mechanism is exactly the same. It's between this kind of dipoles, but one is just the fluctuating and the other is permanent. So when you have liquid element here, they're always having this secondary bonding. When you have the solid material here, you will also have this permanent secondary bonding always. So here is a quick nutshell about all this bonding together. So I feel like this is a good summary already if you would like to know some details and even some examples about them. So we have 3 primary bonding and 2 types of secondary bondings. So you could read a little bit detail here. What we would like to give you in the next is some correlation between this very basic atomic electronic structures. Will they have an impact on the properties? Actually, yes. I could already give you 2 examples. They're not quantitative. This is the shortcut because the material is complex and atoms is such a small level. But they have already some decisive factor in terms of quality. The first example is given on the, let's say, the melting temperature as a property. So, everything has a melting temperature when you change between solid and liquid. And this is the mechanism between here actually is something to break the bonding system. So when you have, let's say, 2 atoms together, they are bonded. If we break it from solid to liquid, we're actually breaking this bonding. There are 2, let's say, variables for the bonding. One is energy, and the other is so-called this R0. This is the bonding length or the bond length. As you can see, if you have a material that has a larger energy, so larger energy means more negative, actually, and it will be harder to break this bonding. Because if you melt it, you need to give a higher temperature to finally become liquid to break this bond. That's why the conclusion is if you have larger energy, you would require a larger melting temperature. This is very easy to understand. If you compare, you can think about the example already. If you compare sand and with some, aluminum, then you can imagine what is the bonding type and why something is even higher to become liquid than the other. And similarly, this is about the thermal expansion. So due to the time, I will not explain in detail, but it's very similar. Basically, if you want to just stretch your material with temperature, when you have a larger energy, you'll be less, you will be a little bit hard to stretch it than the material with less energy. We will also touch this when we really speak about the thermal properties in detail. So now I'd like to give you a summary about our second part. So as you can see, we have ceramic, mainly with large bonding energy with a high melting temperature, high E modular, and smaller thermal expansion, because they're having the strongest bonds like ionic and covalent bonding. And for metals, we have a little bit less strong bonding. So they're the metallic bonding with a moderate melting temperature, moderate E modular, and moderate thermal expansion. And speaking about polymer, and you see everything is low except for the thermal expansion because their dominant bonding is actually the secondary. That's why they're pretty weak in terms of some properties. All right, so the final summary is given here. I hope via this very, let's say, informative and rather dense knowledge given, you could be able to get some memories back from your high school, and you remember what valence electrons, what it's about and why they're decisive. And you also learned there are 3 types of primary bonding, or 4 if you call mixed one is also 1. And how to calculate the mixed bonding. There's an equation depending on the electron activities. And there's also the secondary bonding. As a typical example is the van der Waals bonds. And you could also know this very basic small structure in the atom level is already decisive for certain properties, especially thermal. And you will also learn more. All right, I think that's the end of today's course. I hope everybody enjoyed it. Just a few quick announcements. First, the text corresponding to today's lecture is chapter 1 and 2. And you will have your assignment already open today. Oh, sorry, this is not updated yet. So the deadline will be 6 p.m. Sunday. We don't want you work late until 11 p.m. So finish it early. Remember the 10,000 hours rule. Just let's say a simple thought for you to think about to tune our lecture tomorrow is when you have a stack of oranges, actually you can imagine them as atoms. So, but it's easier to go with orange. And how could you best stack them? You can try to think about it. All right, with that, I would finish today's lecture. So once again, very happy to meet all of you. And I hope we will have a beautiful journey here for the next 6-7 weeks. Good, then I wish everybody a nice day and nice week. See you tomorrow.
Thank you.
Excuse me, I have one question.
Oh yeah, of course. I forgot to say, if you have any questions, just ask.
Yeah, so I was looking at the course page on my courses, and I'm not able to see the assignment page. So like, where do we find the assignments?
It's not open yet, so you'll
okay.
later this afternoon.
All right, thank you.
In the materials page, you will find the lecture slides later.
Yes.
That was, now I lost you. Who was there? Oh, he has already left. Okay, good. All right, so for the rest of you,